Now let's talk about slope of a line. We mentioned in the last sections about slope somewhat with regard to a particular form of the equation, the y equals mx plus b or slope-intercept form. We'll talk a little bit more about that in this lecture and the next. For now, we are going to start our conversation by defining the slope of a line, how we compute the slope, and then working towards our ultimate goal, which is again to still figure out clever ways to graph some linear equation using as little information as possible. So in our examples here, we'll talk about graphing a line given just the slope and one particular point, and as well graphing a line using the slope and one of the intercepts, which really is about the same problem. The intercept itself is just one particular point along the line. So before we get there, let's talk about slope itself. How do we define slope? Slope is basically a ratio of how moving from one point to another along our linear equation changes the rise and run of that particular line. And this ratio of values basically takes on four different scenarios. You can have a positive slope, meaning as the values of x increase, so too does the value of your output y. A negative slope, meaning as x increases, the value drops. And then our two particularly special cases that we mentioned earlier. We can have a slope of 0, or we can have a slope of undefined. Why these two particular forms have slopes of 0 and undefined will be a little bit more clear in some examples we'll show later. But these particular equations have the form y equals a constant, like y equals 2, or x equals a constant, like -3. So slope in this particular example can be shown to be described not as a ratio of rise over run, but even more technically speaking, as the difference in the y values of 2 points and the difference of x values of 2 points. Now the subscripts here just delineate which point we're really discussing. So you can imagine this as, let's say, 2 points along the side of a mountain. Point 1 here at the bottom is where we start at the foot of the mountain. And point 2 is up at the top where our destination is. Now anyone who's traveled, let's say, up or down stairs knows that stairs are steep going up as they are going down. And so we could actually reverse the subscript here to describe either point as being the beginning or end for our journey. The ratio of that distance between them should remain the same. Now let's go with our convention here. So you can see that, for instance, if I were to substitute in for my equation, my numerator is the difference in y values, which is 6 minus 3, and my x2 minus x1 value substitutions will be something like 7 minus 2. And so in the numerator, I get 6 minus 3 is 3. The denominator, I get 7 minus 2 is 5. M equals 3/5 describes the rate at which this line rises to how far it runs forward. So you can imagine as you're walking up a hill, for every step that you take forward, there's some change in elevation. This is what we call the steepness or the slope of the mountain. Now typically you won't be given a visualization of this. It'll look something like this example where we're asked to use the slope formula or to simply find the slope of the line that runs through a couple of points. I could graph these on a coordinate plane and then follow the procedure as we showed a second ago, but more clearly it is to understand just simply that the slope is the difference in y values over the difference in x values. And that rise over run is really all I need to compute the slope. So typically I'll mark one of these as point 1 and the second one as point 2. Just to distinguish, we'll use these subscripts and make our substitutions this way. So my x2 value is positive 4 minus my y1 value, which is negative 3. Be careful when substituting values into an equation like this. When I have formulas that have subtraction in them, there's occasions when you have to substitute a negative value, and people often forget to carry the sign. So that's just a pitfall that I've noticed that you might be aware of. For my denominator here, I need to substitute in x2, which is negative 7, minus x1, which again happens to be a negative value. So in my numerator, I get 4 minus a negative 3. Reinterpreting that, I could say that's the same as 4 plus 3, so we get 7. And in the denominator, I get negative 7 minus negative 2, or in other words, negative 7 plus 2 gives me negative 5. And so my slope, finally, we can say is negative 7/5. So with the negative out front, I can basically attribute that to either the numerator or denominator. In other words, this is the same as negative 7 over positive 5 or positive 7 over negative 5. And the way that you attribute that negative sign sort of changes how you interpret the slope, right? Since we know the slope's negative, it should have generally a decreasing outcome as our x value increases along the xy axis. But with the fraction that we have, I could say, for instance, that negative 7/5 suggests that as we fall 7 units, I would move 5 units to the right. For example, 7 over negative 5, I would then say for every 7 units that I rise upwards, I fall to the left 5 units. Or excuse me, run to the left 5 units. As is the case, this again represents that ratio of rise over run for our linear equation. So given the bare minimum information of a point along the line and what the slope of our line happens to be, we can actually use that slope to get to a second point. And if all we need are 2 points, or maybe 3, to graph a linear equation, this is enough information to do it. So how do we actually perform this? Well, we've got to plot the given point, and then we use that ratio of rise over run because the slope here helps us identify how to get from one point along the line to another. Starting at the given point, you count the rise and run to mark a second, and with enough of these, we can connect the points to create our linear equation. So here we're asked to graph the line passing through the point 1, negative 1 with a slope of 3/4. So here again, we'll start by plotting. And I'll go ahead and give some tick marks here. That's 1, 2, 3, 4. 1, 2, 3, 4. So 1, negative 1 means that we move 1 unit in the x and then down 1 unit in the y. It's going to put me somewhere about here. And what we know is that the slope here represents, again, this rise over run. So if I were to move 3 units in elevation upwards and then 4 units to the right, it looks like I'll land nicely at another point. So this is negative 1. We would move up 1 to 0, and then 2 more units upwards and 4 units to the right would plot me somewhere around here. Sorry. So there we have our first point at positive 1, negative 1. And our second unit would be 3 units up, which put me at positive 2. I would be at positive 5 units and up to positive 2 in the x, y direction. So going from one point to another is nice and easy. We've gotten a crude graph, but we can graph and select our connecting points like this to show that linear equation. So again, utilizing a digital screen is very helpful. With a crude drawing like this, it's best just to get a general characteristic of what the linear equation looks like. Further along, this concept gets more complex if we are asked to, for instance, graph using the slope and the intercept. Here we actually have a graphic that's a little bit better than my hand drawing. But you can see, for example, if I wanted to plot the y equals 1/2 x plus 3, the particular form that this takes on is one that I've mentioned already that is very helpful to us. So as opposed to earlier where we selected particular values for x and substituted into an equation, we could actually use the features of this format of the equation to plot the line much more quickly. By knowing, for instance, that the constant term at the end represents the y-intercept, I can actually plot that point immediately at 0, 3, and then use the slope, the 1/2 here representing that m term, to represent the rise of a run to get from one point to another. And after using a starting position of the y-intercept and plotting maybe 2 or 3 points, I can then infer the line for the rest of my solutions. Now here's an example where we're asked simply to identify the slope and y-intercept. In part A, it's quite simple. The slope is -4/7, meaning for every 4 units down that I fall, I would run 7 units to the right. And my intercept is at -2. And more specifically, we would say we report this as 0, -2 as a point along the x and y coordinate plane. For part B, it's actually not very clear what the slope and intercept are. In some cases, it may be more efficient to actually rearrange this equation such that it looks like the part A form of the slope-intercept type. And so I could, for instance, here subtract x from both sides. I come now to be 3y is equal to -x plus 9. And division by 3 on both sides simplifies my equation now to y equals -1/3 x plus 9/3. I'm basically taking the fraction here and breaking it apart by dividing both numerator terms by 3. So -1x divided by 3 is the same as -1/3 x, and 9 divided by 3 actually simplifies even further. So I could really say this is -1/3 x plus 3. And that would be an easier way to then identify what the slope and intercept happen to be. So here I'm given an example where I have the slope-intercept form. So very quickly I can identify that the slope of this line is -1. And I'll actually go ahead and interpret it as a fraction by putting it over 1. Anytime you have a whole number for your coefficient of x, you can reinterpret that as a fraction if you put it over 1. And that's useful for talking about slope. My intercept for the y component here would be at -1, so 0, -1. And so now we go to our plot. There's -1, +1, there's 1 and 2. So we can plot our point of the y-intercept at 0, -1. And if I follow my slope here, the rise and run, I can again associate that negative symbol with either numerator or denominator. Excuse my dog. I can rise 1 unit and run to the left 1 unit to actually get to another point. Or I could actually run 1 unit and fall 1 unit to get to a point on the other side. So with a few lines or a few points drawn here, I can infer my line looks something like this. So here again we see an example where I have a standard form equation that isn't immediately obvious what the slope and intercept happen to be. And so, like before, we can rearrange. This happens to be the same equation that we saw a moment ago. So it happens to reduce to -1/3 x plus 3. So rearrangement here again is negative 1/3 x plus 3. And so I plot my starting position at y equals positive 3. So now when I move inside the coordinate plane, I start down 1 unit and then over 3 units, which puts me right around here. So I can add some more values here, but generally speaking, we can follow the same pattern. If I go down 1 more unit to 1 and then right 3 units, I'll be somewhere around here. And so now we can infer our line. So there's another example. If we start in some standard form, you can rearrange to solve for y before using the graphic techniques that we discussed.